definitely more technical and more on a derivation part, right?
A little bit.
So if you are, for the undergrad students, it might be a little bit overwhelming, right? So if you really feel that you completely don't follow what's going on, you are free to leave. Don't feel that you have to be here for the how many hours it takes us to finish it. But again, so since we do computational chemistry is not just, or whatever, physics, whatever you call it, it's not just using the software, right? We also, of course, have to know how the things were programmed, were derived. So Levi will really present the way how the data taken from specific software can be analyzed, put together, and getting something new information can be taken from the software based, not just kind of getting the raw data, but really with some additional derivation and I would say derivation, right?
Yeah, a little bit of derivation, not much. And if you have any questions, I don't want you to feel bad if you interrupt me. This is more of a conversation.
It's not a presentation, it's a discussion.
Yeah.
Right?
So today we're going to look at how to get oscillator strengths between triplet states and singlet states using spin-over coupling. If you've taken PChem, hopefully you know that optical transitions between triplet and singlet are optically forbidden because of the spin. It needs to have no momentum, spin change, and a photon has one spin. So it can't switch except through spin-over coupling and other things. So why we're studying this is in reality, you excite and there's a whole bunch of stuff that goes on, and the nuclei move crazily along the potential energy surface, and then so a photon comes in, the molecule gets excited, it goes crazy until it gets to the lowest state. After some time, a photon gets emitted, and we want to predict computationally what energy this photon is emitted at. And to do that, we don't want to simulate all of this. There are some programs that can do excited state non-adiabatic dynamics, but that's super costly. And if we want to do like predictions, this is unrealistic. So
you're probably too fast. Again, thinking about general audience.
Okay, sorry.
So Jaban, I think, gave us a good pace to this. Can you kind of a little bit explain what exactly each of these parabolas or whatever these curves mean? What is your axis y? What is your axis x?
So y is energy. Here is arbitrary units because it doesn't really matter about the units. And then we have internal coordinates. So if we think about like x, y, z, we can convert that into different, we could do like Cartesian, spherical, and I forget the third one. So internal coordinates kind of take the molecule and find which coordinates are the most important to show here instead of having n times 3, where n is the number of atoms, which is not even visible. Like we can't understand it. So that's here. So this is just showing the influence.
So you can call it reaction coordinate, right?
Yeah. So this is showing the influence of the structure of the molecule on energy. So that's what this is. And this is the ground state. So for our case, it's singlet. Red here is excited state singlet. And you'll see most of them are above, all of them are above the triplet. And then the blue ones are the triplet. And I kind of faded them out as we go up because as we go up, they get totally crazy. And then this is kind of like maybe a way that the nuclei would rearrange.
And what is your black line?
This line?
Mm-hmm.
This is excitation.
So you go from ground, you put in electron from the ground state to some excited state.
Yes.
And you put it on triplet or singlet?
So singlet.
If your ground state is singlet, right, so with whatever your spin, you're not changing the spin. So that's why it has to be singlet, because light is not flipping the spin.
Correct.
But when it goes down,
when it goes down,
this time, it can go wherever it wants to.
Yes. So then I tried to show it go along the singlet potential, and then here it would jump to the triplet. That does not necessarily have to occur. It could go along the singlet here, and then here jump, and then go down. But through simplistic view, we can think, oh, it goes.
Okay, it's clear.
Goes down.
And what is your arrow down, the black one down?
So then this is emitting a photon.
Okay, so you excite this, and you emit this energy.
Yes.
How we call this change in energy?
Reorganization energy?
Mm-hmm. No. Change in energy between absorption and emission.
Stop shift?
Yeah, stop shift.
But I thought it could also be called reorganization.
No, reorganization energy, it's a move of your
Oh.
parabolas, like this minima, this kind of change in terms of energy.
Okay. And then if we go from what actually happens to what is like computationally feasible, that's why I have this arrow. So this is what happens in reality. What we're going to look at is a much simpler view. So we still have the ground state, and then you'll see this dashed line here. And for those of you who have not done a lot of organometallic stuff, this is showing the approximation delta SCF. So this dashed line is not the excited state. It is computing the kind of the ground state density using triplet spin. So here we use singlet spin. We can change the spin and mandate that there are 2 extra alpha electrons, which then we can find the density that way, and we can find the approximate excited state. So then we can do the same calculation, do excited state using this geometry, and get out the photon as well. So the reason why we want to look at this is we're working with Bakhtir to do QSAR modeling, which takes data, runs it through like linear regression or higher order things, and it can predict the properties of a molecule for specific properties. And then we can like do a feedback loop where he does his modeling, he predicts new ones, we compute using computation, feed back in and go back and forth. And here, what we want to get from here is the lifetime and oscillator strengths, because both of those can help experimentalists determine if a molecule will be good. If we want an excited state to quickly emit, then we obviously want the lifetime to be very short and oscillator strengths to be high. If we want it to be longer lived in the excited state, we want to increase the lifetime. And then like here is what we are kind of going for. I found this paper recently, and they have a maximum, I think it's like at 830 or something, and we still want to shift further for specific applications. So that's
which molecule this is fermentable datum, right?
Yes.
And which molecule?
It's an iridium complex.
Okay. So this is emission. They see emission at 800.
Yes.
Wave
So
numbers.
820.
So which is in
wavelength.
Wavelength. Yes. And it is which range infrared?
Yeah, this is.
Oh, it's red.
This is infrared.
Infrared. Okay.
So the main reason why we want to get above 800 nanometers is if we do any like bioimaging, it can penetrate the skin, where if it's visible, it goes away rapidly.
So what is the delta SCF approximation that you're making?
So what we are approximating is instead of using the gradients from the excited state, right? So if we start here, if we optimize the ground state, and then we say, let's excite to this state, and use the gradients of the S1 for the optimization, then it has to do T to the FT at every ionic step.
Yeah.
So if T to the FT takes 5 hours and it does 10, that's 50 hours, versus if we just enforce triplet spin and then optimize it using ground state DFT, we can get an approximate excited state geometry and then just run a single TDFT calculation to get the excitation or emission energy.
Okay.
Does that make sense?
I think so, yeah. 'Cause you're just saying that you enforce a constraint on the spin, do the ground state calculation again, but then that ground state is actually an excited state. So
Yeah.
you kind of get
The geometry of the state
Yeah.
is used as.
excited state.
Yes.
Yeah.
And if you run hundreds or thousands or tens of thousands of calculations, running analog OT to DFT is not the best because it can take so much time. And Javed, I'm sure, can tell you if we do analog OT to DFT, so using the gradients from the excited state, we don't know which excited state potential will give us the correct molecule because
they might
if we
switch the order.
excite here, right, we might come way over here, and this internal coordinates might be different depending on which excited state we're on. So we might veer here or here, and depending on where we are, this emission will be different.
Okay.
So that's another reason why excited state can kind of be a little.
The problem with when you find in the minima in excited state, that the minima is not really defined, right?
Right.
Because in the ground state, it's clear. You go into the lowest possible minima, which is really possible. So you kind of know what you are searching for. But when you're in excited state, and you of course can find this minimum of excited state, but on the other hand, at the same geometry, it might be different state. State number 3 now having both states than state number 2, right? And you never know whether they switch or not and what exactly the minimum you are searching for. And this makes this approach kind of very vague.
Yes.
I'm a little lost with some of the lines here. I now understand this a little bit.
Red
better.
is singlet, right? Blue is triplet, or what is
you
it?
mean lines or arrows?
Well, I mean, I'm looking at this, and you're explaining this fine. Where are
Okay,
this for a
so-
specific guy? How's this relate to that?
So this is an experiment. This is what we typically do. We want to take what we typically do, feed it into QSAR,
Correct.
and QSAR then can tell us different things about a molecule.
So are you going down to that figure? Then?
This is an example.
This is
of what we
observables.
want to do,
Okay.
right? So we want to start out with something like 2, so this red line that has the maximum at like 750, and we want to shift it to higher wavelength
Using this.
using this feedback loop, where we start with theoretical, we give it to QSAR. QSAR predicts new molecules that have better properties. They feed it back to us. We compute it. We give it back to them, and they can give it then to experiment, or in this case, reality.
Who are you presenting this to a general audience or to?
This is just
For us.
There's not for any like
This-
conference
yeah,
or anything.
He's
just
not
for
training
us.
his talk, it's just a discussion of
Okay.
things which he's doing.
Yeah.
This is just a suggestion.
Yeah.
To make it less busy, it'd be interesting if we started with this and then we went to the thing you wanted to do and then back to this, like
Sure.
almost splitting it up into 2
Sure. Yeah.
slides. That way, the reader, for me, it's like, what are you doing? Wait, we're here. Okay, there's
Okay.
And I'm spending more time reading this than listening to you, and
Yes.
Well, indeed,
So
indeed, this slide has to be probably split it into 4
Four?
slides. 1, 2, 3.
yeah, I don't
okay.
think so. Yeah,
Each figure probably can be
Okay.
there's
explained
a lot
on
happening.
slide 1, slide 2, slide 3,
To
slide
be
4.
quite honest, I looked at this and I got scared.
Oh.
I was like, what happened? Did someone have a bad day? That's kind of like.
No, I don't think they had a bad day. So that's what we want to study.
Yeah.
I got there.
Oh, it's flying away.
So the goal of this presentation, hopefully after you guys understand how to do perturbation to get oscillator strength from T1 to ground state using spin-over coupling and the energy of that, understand how each one of the terms in the perturbation influences the energy and oscillator strengths. Through this, later this will make more sense how we introduce the number of states into the perturbation theory and how that influences, and then from literature, they don't really talk about applying this to higher triplet excited states other than just T1. And we'll talk about that at the end. So first, let's talk about just slightly hit perturbation theory. I don't want to go super in depth on it. So perturbation theory is a theory that we use a Hamiltonian that we know and we can solve, and then we add a slight perturbation onto that Hamiltonian. And we can, this is like the solving the Schrodinger equation for the known Hamiltonian that we can easily get. And then this is using the perturbation. So this using both. When you plug that all in, you get 17.6 here. And I know this is super, super complex. The nice thing is we can solve 17.6 in orders of epsilon, which we can look on the next slide. So here's 17.6 again. And if we look at epsilon raised to 0, that's this term and this term, right? And then the wave functions. And it's the standard Schrodinger equation, which Gaussian can solve, or whatever program we need to solve. The next order, first order perturbation, we get the perturbative Hamiltonian onto other states, and solving using Dirac notation, we can come up with E1, so the energy of the first order correction is this, and then we plug them together and we get this.
Levi,
Yes.
is there anything that we could cut to make it make it font bigger, or you need every single step to show?
Really, we need this here.
Okay.
This is, you can just open the book and read it, right?
Yeah,
And
that's.
I just didn't want to go into.
We're not going to the lecture, right? So
Yeah.
we're assuming that he just kind of overviews the perturbation theory, which you're supposed to take in the frames of quantum mechanics.
Yes.
If you didn't take quantum mechanics, just wait. You will take it.
Well, no, I mean, if you want to show the slide, you could do literally in 3 steps. Something like final answer.
Yeah, I put this in just so that people have perturbation back in their brain if they've ever.
Oh, okay.
Which book you used? It looks like you just took
I
a snapshot.
googled it off of this website.
Perturbation back in the brain sounds
Yeah.
nice.
So how we use perturbation.
But again, return to the final answer and go term by term. What exactly your E naught?
So this
people can
E
understand.
naught here, or if you look at this screen here and here, this is the non-perturbed energy, and then we have the first order correction here. So we have a wave function, an expectation value with our perturbed Hamiltonian with the non-perturbed wave functions over the value of the overlap. So that's this term. So this is the second order, first order energy correction, which is shown here. And then you can go higher and higher in terms of epsilon. So here there's like epsilon squared. So you can do more, but for overview, this is.
But each term will be smaller and smaller than the previous ones. That's why you're assuming that this contribution is very small. And this called perturbation theory, right? The main approximation requirement that your perturbation should be much smaller comparing to the regular term in your Hamiltonian, which means that this additional term is much smaller than your E naught, right? If it's backward, it means you're not in the right regime and your formula will be not really applicable.
Yes.
Means you will have a big error if you apply this, because it's approximation, of course, right? It's
so
not the accurate thing to do.
if we want to apply perturbation theory, this V Hamiltonian that is shown here will be the spin-orbit coupling Hamiltonian, which right now I'm using QChem to compute the spin-orbit coupling matrix elements for various.
And what is your E naught?
E naught is the triplet energy. It's here. Yes.
So B is Hamiltonian or
Hamiltonian. H is the one that we can solve for. So this is the, like if we do singlet triplet stuff, this would be the typical electronic Hamiltonian, and then this would be the spin-over coupling. Right? Otherwise, it doesn't make sense to make a Hamiltonian and like potential.
Technically, she's right. It's potential.
Okay.
Because you do a correction for the potential energy.
Sure. What's your bet? So if we look at this expression compared to, I took this from this article. So this is the zero order term, which is just the energy of the first triplet state. This is the first order perturbation, and then they do second order perturbation theory for this particular implementation. And here we see we have our matrix element squared over an energy. So both of these terms are in terms of energy, so we get energy squared over energy, so then that just gives us energy. And they never noticed this, maybe, but they flipped their signs here. So I believe that the pipe should go on the outside of the less than sign. And then we have this delta E. And the second order term is very similar to the first order term, but instead of the singlet state, they do the triplet state.
This is not a second order. It's the same order term. It's not a second order correction. It's a first order correction to the different
Yes. So,
energy, because you have singlets and triplets, right? So one term showing you first order correction between singlet triplet, and the second one between triplet.
yeah.
So it's not the second order, it's the first order.
Jabet and I argued about this the other day, and the paper called it second order.
Wait.
It's not second order in terms of perturbation theory.
Just a second. In second, not in the first, second like interval of time. In your previous slide, you do show correction in the first order.
Mm-hmm.
It does include matrix element of the perturbative term in the Hamiltonian, V.
Yes.
Bra, V, cat,
Yes.
equals E sub 1. In the denominator, there is nothing. Your psi naught, Brian cat with psi naught, is 1, is normalization.
Yes.
So there is no nothing. It's just matrix element of the interaction Hamiltonian. If you would continue recursive procedure for second and so on corrections, the second correction to the energy will have the energy difference in the denominator. Right? So if you do see something with energy difference in the denominator, and it is assumed to be correction to the energy, it is not the first but second.
Okay.
But then both are second order terms.
Yes.
So then this has zero order, no first order, and 2 second order.
The equation looks this way.
Okay. And later on we'll talk about the relative strength, actually right now. If we look at each term, this first one, we can look at the relative magnitude of the denominator and numerator. No, I forget whatever they're called. So if we look at the matrix element, if that's much greater than the difference between the singlet excited state and the first triplet excited state, this will have a relatively large energy difference correction. If it's the opposite, it should be relatively small. And this is also the case for the triplet. And it is worthy to note that for T1, the energy will always go down. So if you do if you do spin-over coupling using perturbation theory, for T1, your energy will always shift down because T1 is always less than S naught, and T1 is always less than any other excited state. So that's important, and keep that in the back of your head because later on that won't be the case, and we'll see that it's problematic that it does not follow these kind of things.
What is TN again? Is there an initial?
Any
TN,
triplet state higher than 1.
Okay.
yeah, so we're doing a double sum over all excited states except T1,
Okay.
and then over the different spin components.
Oh, the boxes were covering up.
Yeah,
Okay, that's
I
not-
should have not put that there, but
It's like,
sorry, my bad.
that's okay.
So yeah, and it is also important to look at. We do this for all 3 spin components. So if it's
Before you go to this one, so again, if you just do regular Gaussian calculations, who all of you already familiar with very well, right? So you can of course calculate singlets, you can calculate triplets, or you can calculate both singlets and triplets as one run, and then it will give you all these levels, what you need, all these energies, right? But either doing singlets or singlet triplets together, neither of this calculation really includes the spin orbit coupling when you do Gaussian, right? So technically, you need to do something to get the spin orbit couplings first, which is this HCO indexes, right? So this is a coupling which couples the singlet and triplet state to the spin component. And unfortunately, Gaussian software, which we're all very familiar with, doesn't really have this feature. We cannot get the spin orbit couplings from Gaussian, but there is some other software which allows these calculations, right? So technically, you can imagine that you get just energies of all singlets, 1, 2, 3, all triplets, 1, 2, 3, 4, and so on, right? And of course, ground state as well. And you also, if you're not using Gaussian but some other software, it also gives you the spin orbit couplings like this HSO matrix element as an outcome of the software, right?
yes,
So technically, you can have all these initial things in these formulas, in these terms. Now the question is, how can we really combine all this information together to really correct the energy according to the perturbation theory, right? And this is kind of formula which gives this,
yeah.
make it possible to do, because if you know your ST and this HSO in between, right, you can just calculate these terms, add them together, and you will be done. But there's also, when we call triplet, right, it means you really have three states
Yeah, so here.
with different components of spins, right? Can you, oh, it's there. Can you go to the next slide?
So we start out with like a hydrogen-like atom. If you add another electron, you can go into singlet, triplet, and then it makes it non-degenerate when you add the extra electron. And then this also has spin-orbit coupling interactions, which then split the energies even further. So then we get 3 states per state for triplet, and then for singlet we only get a single state because there's no change in the spin component.
But is it really included in this formula?
What?
The splitting in triplet state?
Yes.
Where?
So the energy of I, which I don't really like how they implemented it. So this E of I means this is I is the spin component. So this term never changes, but the coupling matrix here is dependent on
But
I.
no, it doesn't have any dependence on I.
T1I.
Oh. Uh-huh.
And then the bottom that has no spin component, and then J varies over the spin, so it's
Which values I can take?
I can be -1, 0, 1. I can be -1, 0, and 1.
So this is.
So like magnetic.
Yes.
Okay.
Yes.
But where are you getting this Ti?
Ti.
T with the index I. Because again, if you Unperturbed case, right?
No,
Gives
but
you just one singlet and one triplet energy, which is supposed to be 3 times degenerate.
the spin-orbit coupling matrix has different spins.
Yes?
So it outputs the matrix element.
No, you don't have its. You're saying the program
The program
already gives you the matrix elements.
for
3 of them, where it already includes the
Yes.
splitting in this spin components
so
with
you
I
take
index.
this from the program.
So you're not taking just HSO term. It really gives you the matrix elements already.
Yes,
Kind
it
of,
gives you.
It gives you already
the
the
coupling.
piece, which is even squared, right? So it's really
No,
gives
no,
you
it's
the-
not squared.
Whatever. You need to square by itself, but it gives you really like
Yeah.
numbers of this each matrix element
Yes, it gives you
with
this.
different components for I.
Yes. So the program gives you different spin components, and for the triplet, it gives pairs.
Wait. I'm just feeling back. It's not spin components, spin projections.
Oh, sorry, yeah.
Like
Spin,
components would be alpha and beta, and your projections are
yes. So the
Semantics.
0 plus minus 1.
This is semantics. Yes.
Sometimes important.
Projection.
yes. Sorry, my bad. Yes.
So here, from where production comes from, spin-orbit coupling.
Yeah. So the spin-orbit coupling. So
So,
these are the corrections. So the spin-orbit coupling.
so first correction, the second term means correction for singlet.
So it's the interaction between singlet and
Have a
triplet.
good weekend.
So
The
as
third
well,
term is
So you come
interaction
Tuesday, right?
between triplet and triplet.
what I
I is spin projection. J is another spin projection, right? Because you have the projection of -1 interacting with 1, 0, or -1. So if we look at how many states, let me rephrase that. If we look at the function of number of states to energy perturbation, this is what it's showing. So this guy is from this compound here, and I could have put all of these on, but it would have just been way too much information. And the other one, so all of these guys here look very similar to this. And the reason I put this up in contour plot is the energy should monotonically decrease. Because if we look back at our formula, this energy difference is always negative, this energy difference is always negative, and when you add negatives, you don't become positive. So it has to monotonically decrease.
But just a second. You have 1, 2, 3, 4, 5, 6 different compounds, and you
Yes.
have 2 plots. Which one?
So
Which
the,
of these plots corresponds to
the
which
left
compound?
hand is this one, the right hand is this one.
So you from these 6 you've taken only these 2.
Yeah, because most of this compound, this compound, this compound, that compound, and this one look very similar to this.
Okay,
So to put in all of them would just be way too much information.
fine. But so you start with the first and the last,
Yes.
and right is your first, left is your or backward, whatever.
So if we keep number of triplet states fixed, varied, but we keep singlets fixed. So if, let's say look at 10, they always decrease as you go up, and it's the same if you go across. And on this side, it's also the same.
And again, decrease, increase. Your largest number is red, and the smallest is blue or backward.
Yeah, I should have made them bigger. So this is the smallest number, this is the largest. So as you go diagonally, it goes down in energy. And the difference in energy is around 0.05-ish. So the perturbation is very small.
Can you overlay the images on, make the things bigger and overlay the structures on the areas? Like, for example,
Why would I want to do that?
I don't know, would it be beneficial? Because I'm kind of confused what's...
Well, this guy doesn't really relate to the structures. He said, like, first, okay, explain again what is you are really showing on
So
this
this
figure.
one
It's
is
number
like this.
of state on your y-axis.
Oh yeah. So this is number of singlet states. This is number of triplet states.
Which means you can also put energy, because you understand, like singlet one, state number one has this energy, and of course state number two will have even higher energy, and so on.
Energy.
So that's why going with a number of singlets, number of triplets means you go kind of energy up for singlets, energy up for triplets,
Got it.
right? And if they have the same energy, this is what you have on the diagonal.
Okay.
Yeah. So it would be n.
Oh, okay. Okay, yeah.
Ah,
Right.
yes, good.
N.
So this numbering n is what you have on your y and
Yeah.
y
So-
and x axis.
One n would be, so this would be x axis and this would be y axis, right?
Mm-hmm.
So then, like if we keep,
Levi, just a
Yeah.
second. Is it upper limit of this summation?
yes,
So the larger your, so to say, basis set, the you get difference in results.
yeah,
What- so your x and y are upper limits in your summation on the previous slide.
correct.
Thanks.
And we can see it's somewhat dramatic for this one here. So then,
The more turns
Um,
he's taking, the less
oh, I-
energy he's getting.
okay, so this one I reversed because later on I realized
you have-
what I was doing was not taking the energy
Single triplets.
difference this way.
Right? So you
I took
couple them,
Sn
they
minus
go
Tn.
something like this,
So,
right?
There was a negative sign.
And
So this
this
should be blue,
splitting
this
is
should be red.
reducing if he's
So it-
put more and more
that-
couples, couplings.
In the first figure is kind of like, I mean, no, that's fine. No,
Oh, this one.
it's kind of showing the like diagonal relationship between these two.
Yeah.
Other one is kind of blocked to the
Yeah.
one. Quite very fast.
So what I think it would imply is up until we get to 10, triplet, there's nothing. So the coupling is very very minimal, which probably means that the nature of the triplet state compared to the singlet states are vastly different. So when you do the spin over coupling calculations, you virtually get zero.
Up to certain
Up until you hit a certain number, and then it changes because
Oh.
from 0 to a number has a straight line, and then it kind of doesn't do anything.
So again, your blue and red scheme showing not the splitting between levels, but the energy
The energy,
of the total energy of this state.
yes,
So
of
it means
T1.
the blue one means it's not that your singlet triplet has less splitting. It means that your singlet is moving low.
The triplet is
The
moving
triplet
down.
is, I mean, the first state, wherever it is, we cannot say singlet or triplet. It's really moving down, comparing to the not perturbed, not coupled spin orbit couple. If you're not including
Yes.
spin orbit coupling, it will be much higher energy. And if you put more and more terms, it's really going more and more
Yes,
down.
but
Not kind of in a linear way, right?
yes, but so the one on the right, left, sorry, blue is 1.737 and red is 1.759. So it is
So it's
very,
not very big difference.
very small difference.
Well, we see the trends, but actual energy is of course not like 2 electron volts
What
down.
is the degenerate
What?
without
What?
spin
Repeat again the question.
What
Why?
is the energy of T1
So-
including
Ah.
spin orbit?
That would be very, very close to 1.759. But I didn't memorize all the raw data. So
And this is your data
yeah,
or someone else?
I calculated.
Ah, oh, okay.
So, and we have QChem for another month, and then the trial goes away. We might be able to do some manipulation.
Does it go to group or to the user?
That I'm not sure. I need to look at.
So we-
I
we
could
can
do
switch
it.
that
And
See how many people in the
then,
room?
like Jabed could do it. And,
Or even if not, then we can switch
Yeah.
to his group, right? Then
Yeah.
probably you have NERSC account, right?
no, this is not on the.
No, I
You
don't
just
have yet.
request trial version.
Oh,
I was planning to apply for that.
Okay. So actually, we have another
Yeah.
2 months at least for Dimitri's group, another 2 months for Bacteria group. Then we can ask probably Andrei Krzyzewski. We can ask the whole department.
So now we kind of understand a little bit about the energy correction. So if we go back here, the spin-over coupling is important. This denominator is important. Later on, when we go past just T1, we'll come back to this energy difference because this energy difference can get very small, which means that it blows up and then bad things happen. So if we look at the oscillator strengths, we have to compute oscillator strengths for each projection.
Slow down because we not follow your. You are too quick for us.
Or we are too slow for you.
Oh.
Oh, you, yeah.
Okay, so I left the 1.10 on because 1.10 is the input into the actual oscillator strengths. Before we can get oscillator strengths, though, we have to compute the transition dipole moment, which has this.
But I have an issue with your calculation of where did you. This is just what you do.
What? Which line?
Last line.
This-
The
this
last
one.
formula, right?
Yes.
Because technically, if you when you calculate the transition dipole moment, you need the wave function. And if you correct the energy through the spin orbit coupling, the wave function also has to be corrected. So this mu, which you use as transition dipole moment, where do you get it?
So
Is it-
this mu,
Yeah.
that is the output from
With
QCAM
spin orbit couplings.
without.
Here's an issue. You correct energy without correcting the actual dipole moment, transition dipole moment. Because your wave function, when you include spin orbit coupling, like you showing for your formula, you just have show, like if you go back to the perturbation theory, you show the correction for the energy, but you miss the correction for the wave function, right? Because it's also, of course, you get the correction to the unperturbed wave function plus
Yes.
same kind of portion as you do for energy.
Yes. And
And it looks reasonable. If you correct energy, you also need to correct the wave function, and then you correct your oscillator strength not only through the term which goes through the energy, but also transition dipole moment by itself has to be corrected due to the new wave functions.
yes. And through literature, when I was reading about this, I'm not saying you're wrong. You're
And this
totally
is
right.
formally
Yes.
how we should do.
Yes.
But maybe it's too complicated. Maybe you can simplify it.
So what?
So then at least people should compare.
Yes. So what they say is the triplet state is borrowing the brightness.
As what? Borrowing.
Borrowing brightness. So it's kind of saying if we couple the triplet states to this, like if we compute the transition dipole moment for triplet to singlet, that's 0. So if we couple triplet to triplet, then we almost get 0 oscillator strength. But this is what I have thought from what they're saying. So this is saying,
Again, small correction to your Hamiltonian not necessarily would be a small correction to the wave function.
yes,
And again, go to the chapters in the book and some examples how this perturbation theory is derived and is applied in very simple cases like particle in the box or something like that. So I don't buy this argument as an argument, right?
okay,
Even if your unperturbed term for the wave function would be small, the correction in the wave function can be pretty significant
okay.
and still will be valid for the perturbation theory.
I don't know why I put a box around there.
No. The box, I do not see the whole picture, but the box looks reasonable. I like the box. So the energy is corrected to the second order, right?
Mm-hmm.
Yes.
And then the first order correction to wave function is nothing. It is not correct. It is getting changed only in the second order.
Mm-hmm.
And for the second order correction for the wave function includes energy difference in the denominator.
Mm-hmm.
So what is shown inside the box looks like second order correction for wave function.
Oh, you mean the
Yes,
outside the
yes,
box, not
yes.
inside?
So I
Outside the box.
the see this mu ms not mu ms not seems unchanged, right? And then this t sub 1I and all this stuff may look like a perturbative expression of the second order for t1 sub I.
Well, but I would definitely probably make this missed steps for the checking that this formula really includes the correction to the
I don't
perturbation
know how
to the wave function.
I could go about doing
Huh?
that.
You
Not
don't know how to do it?
No.
What do you mean?
QChem doesn't give us the wave function.
No, the point is not based on the QChem. The question is, if you just take these formulas, following the rules for the perturbation theory and just correct, like write the correction for the wave function, write the correction for the energy, which you already have, like we don't see the correction for the wave function, but you have it for energy, to the second order, and second order correction to the wave function, right? And kind of then using these corrected guys, plug in to calculate the oscillator strength, the transition dipole moment, right? Kind of this one, which Dmitry is saying that technically this result is already implies the correction to the wave function.
Okay.
Like, although we have the singlets, but contribution from these terms looks like it's already inside, like it just was done as a final stage.
Yeah.
I suggesting to really do it step by step and to be sure that yes, if you really do it like corrected wave function overlapped with your new, right?
So algebraically.
Yeah, derived in
derived,
right?
Yes. Okay. I thought you
Unless
meant
you
like
really get
No,
in
no,
this
no,
formula.
no. Deriving.
Derived.
yes. Okay.
And it's a good chance that you end up with this, with the final result of this, which just convince all of us that yes, this already includes not just correction to the energy, but also correction to the wave function.
And then we can also get
Probably if you just write the correction to the wave function based on the perturbation theory, just looking at it, we already can figure it out without even derivations.
so if this one is looking at the radiative relaxation, which is important because, as I was talking before, experimentalists might want to look at trends of the radiative relaxation with the oscillator strengths. So if we look at this, this should also monotonically this should increase monotonically with the number of singlet states. So here we see that they are very they don't vary along this axis; they stay the same all the way up. So instead of doing a contour plot, we'll just look at leaving just at the singlet states, and we see that that's not happening. We're not monotonically increasing, which means in my code,
Why it should be monotonically increasing?
because this term here could give it a negative sign. However, it's square. So every term should add, not subtract. So if you do a sum of positive numbers, if you increase the summation index, so like if you say vary n from 0 to 2 versus 0 to 10, it should always increase. Right? So if I write right? Actually, I'll just do this. It's not equal. It's always less than, right? So if you sum positive numbers,
Or if your x is positive, if you put absolute value for x.
So x doesn't depend on n?
Well, xn, but it's the absolute value of xn, means it's always positive.
right? So if you have a function, no matter what the function output is, if you take the absolute value, the more numbers you put in, the bigger it should get. And you can never go down. So that would mean that I have a bug in my code. So I need to sit down. I'll probably sit down with Javed one day and try and figure it out. And it's not ideal. So it should monotonically increase, but it's not. I need to figure that out.
There's nothing that would cause your early terms to change by increasing the maximum index, right? Like if you increase,
всегда квадрат.
your summation, instead of going from 5 to 10, your 1 through 5 terms, those don't change at all? There's nothing that could cause those to change?
No, because these terms, like these are not dependent on a number. It only depends on which number it is, right? So if we say S1, S2, S3,
Yeah.
this is set in stone, this is set in stone.
But it wouldn't mess with your Hamiltonian or anything
No,
like that?
no.
Okay.
Because all of these are outputs of a calculation, and all we're doing is like post-processing.
Right. So I'm just wondering if, maybe if terms get manipulated and some of your earlier terms end up shrinking, then you actually aren't guaranteed monotonic increasing.
Yeah, so the values are taken from one calculation. All I'm doing is truncating the maximum.
Okay. Yeah.
Right? So it might change if I vary the number that are calculated, but if I only truncate the terms, then I don't think it should change.
Right.
So can you again show your function which you get? So it's really going down. It's not just not linearly, not monotonically, but it's really,
it
really
jumps down.
even goes down.
It's going down.
Yeah, so I must have, when I was using Python, I must have had a variable mess up or something. So I need to sit down. I realized that this morning, and I was like, oh, I don't have time to fix this because...
So it looks more like a problem with, not with the formulas, but with your coding.
It's
The
a
coding
coding,
itself.
it's pretty...
Okay.
So, because it should monotonically increase. However,
we need a photo of this part.
We do. Have it rolled around stuff.
Huh?
Granted, through our knowledge of mathematics, we know that the contribution for higher excited states should rapidly fall off because the energy difference is getting bigger. So 1 over the energy difference should kill the contribution. So hopefully, when I go through the code again and find the bug, we'll get a nice
Why energy
monotonic.
splitting is
What?
getting bigger?
What?
Like you mentioned, energy splitting getting bigger with increasing energy?
With increasing singlet state. So like
Number of the things.
if you take delta, if you take the difference between T1 and S1, that would be smaller
Oh,
than
you mean you fix your S and you look not on the nearest
T
neighbor splitting.
and
Oh, T.
various.
Because you go higher than the splitting is growing. Okay, yeah.
So it should it should kill the further terms. We just need to figure out how many terms we need to include before it saturates. So that's kind of understanding perturbation theory. And now we're going to go on to, can we apply it to higher triplet states? And I'll tell you right now that I don't think we can, but let's look at the data. So as I was talking before, the energy difference are super important, right? And for T1, the energy difference are always negative, which means that the energy of the perturbed state goes down. But if we go to higher states, then the energy can be positive, and the energy difference can be positive, and things can shoot up. But the more problematic trait is if we look at the absolute value of the difference, we can almost approach 0, which then will imply that we will have infinity, and everything goes to junk, because Svetlana already said perturbation theory, your perturbation has to be small. So if the second term is approaching the magnitude of the first term, everything is gone. So we might need to go from non-degenerate to degenerate if we actually care about absorption into the triplet state.
Question:
Yeah.
Did you confirm that?
What?
When Svetlana,
I'm going to show
oh,
it
okay,
here.
okay.
So if we look here, all of these, this is comparing from the dashed line is Gaussian, and the
Есть
solid
специальные
lines are
теории
QChem.
возмущения,
And the
которые
thing that's
чтобы
important
не
is
было
this
знаменательных нулей в
blip
знаменателе.
here. So this is from the
Just a second. Previous you about degenerate. It is true that there is a different mathematical approach to the perturbation theory, which includes the degenerate states.
Yes.
However, in your computations, it's impossible to get degenerate state.
Yes.
So because of the numerical issues,
However,
you cannot get exactly same energy for different states, right? They will be split by at least a little number.
yes, a little number, but that could cause massive shifts. Because I would agree that you cannot have degenerate triplet states or singlet states, but you may have a case where triplet states.
Oh, singlet and triplet come in the same energy, yeah?
Yeah, so here, this term can become degenerate.
The red one.
This one,
The
I
yellow
agree,
one.
can never be
Exactly.
exact. So like we could have, so singlet, and then we could start here. Right, and these guys, D, E, could approach 0.
Okay.
Right? Which is the reason why I believe for.
But it's very easy to see whether you have this case, like how degenerate your.
Yes, and I'll show some graphs on that. So here, this is not the lowest triplet state. It is a state up here, and it gets massively shifted because of the energy difference approaches 0. So if we, oh wow, that does not look good up there. Let's look at this one because we can actually see a little bit. So this is one compound and this is another. And the thing to look at is kind of the magnitude of this graph and which color. So if it's blue, it's negative. If it's yellow, it's positive. And we see this very big blue peak here, which is from the compound that has the big shift, and it is this coupling term to the perturbation that causes the energy to shift dramatically because it is negative 5,000 eV, which is huge, and that's 1 over, so that's the product. So if you have a non-negligible matrix element times 5,000, you're going to be shifted crazy. And we do have large ones here that are positive, so this is like 3,000, but that was shifted higher in energy into the more dense spectral lines, so it doesn't really show much there, but we do see for this guy that this one causes a huge peak. And then this is looking at the coupling matrix. This is going from the singlet to triplet, and we see, and this is in wave number, so it's about 8,600 times smaller than EV. So like
your scale for splitting in energies in electron volts.
In electron volt, or in inverse electron volt, I should say. So the coupling here are relatively small, but with the huge, it's like 5,000 times 8,000, so like 4 million, I think, 400,000, something like that. That change dramatically shifts it. And these are kind of all the same, so I stopped making them because I was like, it's not helping at all. So then I just looked at the max and min. So the singlet ranges from about 160 to 1,300 wave number, and then the mean is about 1.3. So on average, they're not really doing a lot, but when you get a small energy difference and a large coupling, you get massive changes. And through this, we can't really apply non-degenerate perturbation theory on higher triplet states, which to me is not that bad, not that big a deal, because the real reason why we're doing this is to look at emission, and emission really only matters about the lowest triplet state. But we might want to come up with a way to do degenerate second-order perturbation theory for the spin-over coupling using the spin-over coupling matrix elements, and that could also be something interesting to study.
But first we need to figure out when your function will go to separation.
Yeah.
For your-
So like I think the
for your
first
bugs.
we need to figure out T1, and then later we can think about it.
Was that the goal then, to figure out the T1?
Yeah.
Okay,
But-
because I was going to ask you what was the goal now, because I think kind of, did we diverge? I don't know.
Yeah.
Do you have your data which you calculated and you discussed last time with just absorption spectra with inclusion spin orbit coupling? You remember?
This.
Oh, was it this? Yeah. So technically, this is absorption spectra for which? Can you again
So this
briefly
is
say how they are different?
the different molecules. So this
Oh,
is
those
1,
6
2, 3,
molecules.
4, 5, 6.
Okay.
And I can go back to the structures, but I don't think it
And at least for one, we have really kind of unrealistically shifted
yeah. So
Low's
this one.
transition, which we know we know experimental data for each of these absorption spectra, and we know that nothing happens around 1 or how many, wherever this
Yeah.
value is, which already given us some hints that something is wrong.
Yeah.
So, to your question, we just applied this approach, calculate the absorption spectra,
Mhm.
compare with experiment, and we found out that if other ones more or less okay, at least this middle one really doesn't agree with experiment at all.
Okay.
In this range, right?
Mhm.
So giving us some ideas that something is wrong.
Okay.
And then the question is then what is wrong?
Right.
Like why the methodology which was already published, right? People already use it. Why is it not working in our case? And
And then you're going down these avenues to try to figure out
yeah,
why.
Yeah. And
where the mistake can
where-
happen.
where-
And looks
okay.
like it's really probably this energy degeneracy
energy degeneracy,
cases.
because that just is almost a delta function depending on the state. And if you look, so the blue here is the triplet absorption. So taking the triplet oscillator strength, broadening it to the Gaussian, and then plotting it. And most of them are zero. Like you can barely even make out. Like here you can see a little bit. Here maybe a little bit. Here is obvious. So it doesn't really add anything to the absorption spectra, which is one reason why I say let's just throw it out and only look at T1, because it
It's
doesn't.
only for emission.
Yeah, it doesn't really do anything for absorption.
I mean, in this results that you're comparing, if this was an experimental paper that you had found, or
No,
experiment-
we did this.
okay, so this, okay,
So this is.
no, I meant like you.
This
you
is
were-
our results for
Right.
the molecules which were synthesized by Weifeng, and we know the experimental
Thank
data
you.
from.
That's what I was.
Weifeng.
Yeah. Okay.
So
okay.
like I didn't put an experiment because it would be too busy.
Can you kind of two Mary's questions? If you go to the one of your first slides where you have all this motivation
Oh,
somewhere, slide number 1 or 2, I don't remember.
I don't know what just happened.
Next one, I guess, right? Here, previous one, or next one, where you have 4. Well, this one, right?
Yes.
So actually, this information is from someone else's paper, right?
Yeah.
And this one as well.
Yes.
But then all the data which he was showing, it was really for something which we do for our research.
Okay.
Except the formulas. The formulas
Well,
were taken from everything.
Formulas, yeah.
That's why I agree. Splitting it up and maybe adding a little bit of words would be helpful. Just me. I mean, might be helpful to others.
Yeah. So to conclude, I think I already started, but for this, it appears that there's a bug because it's not monotonically increasing or decreasing. The current methodology is only applicable for T1. We might have to go to degenerate spin-over coupling perturbation theory, which probably won't ever happen. But if we want to look at higher states, that will probably need to be done. And then Peng used a different software. If you don't know Peng, he was a former graduate student here, and it did minor changes, which I also see. And then the main thing is we want to do emission through Delta CF.
What is the code for the NW? Not NW. What do you use NW?
QChem. So there is different than like Galaxy because if you buy it, it's a site license. So if you buy it for one research group, which they specify like it's like 4,500 for as many nodes as you.
4,500
Yeah.
for forever or just for the?
Forever for that version.
Then it's very similar to what we have with ADF, right? Or
No,
ADF
no,
is having annual.
That's manual.
QChem for unlimited processors. So you can use.
It's unlimited process, unlimited time for this
But
version if
for
you're not
one-
moving to a new
for
version.
one
Yeah.
group
Huh?
only. For one research.
But one group, well, same kind of we have with BUS. Right? So it's also license works only for the group of 6 or whatever the limit of the group.
It's not limit of number, it's just a say assigning a group. So you can include like 50.
Oh, okay. So like, I guess it was $38.99.
No, not.
Yeah. And then
But,
like,
but at least it's not annual, right? It's not like
it's not
we
annual.
need to pay
Yeah.
this money every year.
It's not annual. They do a lot more updates than Gaussian, which, like, if you go through like a contract with them, you can get the updates at like a reduced cost. But they have everything we need, so we wouldn't need anything really. Yeah. Yeah, that's about it. And when we do the emission stuff, it would be nice because we can do, if we can get away with like 10 of singlet and triplet, the TVFT calculations would go much faster because we don't have to diagonalize huge matrices. Yeah. So if there's, yep.
Okay, yeah, I just don't know, but is this calculating these 100 singlet transitions, is this going to be costly in terms of time? Or is this pretty quick?
For these ones, I did like 60, but we can see from here they already start to fall off, right?
Okay.
So if we think we need like 100, it would probably take like a day and a half on like 44 processes.
Okay.
So it's not that time consuming, but it is for spin orbit coupling because you have to do all of the coupling matrices, which have the spin projections. So you have to do singlet onto the 3 triplet spin projections, and then you have to do triplet on triplet, and that would be like 9.
They're using Gaussian to do all this, right?
No, QChem.
QChem. Can you do open NPI or MPI kind of things to help with that, or does that not applicable? in this case?
So I think you can, but not with the trial. I don't care to like spend half of the time trying to speed it up. I would rather just run calculations.
Okay, just curious.
So yeah.
But in terms, if you compare, like, including spin orbit coupling calculations with QChem, or whatever it is, QChem?
QChem, yeah.
Comparing to no spin
Oh,
calculations
it's like a
in
third.
the QChem,
It's like a third of the time. For without,
3 times longer.
yeah. Because
But how is, if you're not including spin orbit coupling, how the calculation in the QChem is comparable to Gaussian?
I think it's about the same time.
Okay, so the software by itself works in the same level as Gaussian, but it has this extra feature.
Yeah, and due to all the computational
But
costs.
QChem
And did
also
you
is
check?
not good in
Did you check
parallel.
whether? Did you check whether games have spin orbit calculations for the? I mean, similar, because I think they should have very similar thing as QChem is having. No,
I haven't looked at that yet because I
I
saw.
assume they had a spin orbit only.
Well, in a ground state,
In a ground state.
or maybe it's the same as these guys have it. for
Yeah,
themselves.
I'm not sure. We
Well,
can check.
recheck it because it's again free software.
Yeah.
And again, if you return back to NWChem, it gives you spin orbit only in the ground state, right? You cannot get spin
No,
orbit.
that's Zora.
Yeah, when Zora
NWChem has Zora in the ground state.
But for is it doing the same thing?
It's a relativistic
But can you do the same calculations in the NWChem with
Oh.
spin orbit in the first order perturbation or whatever, second order perturbation? No.
No.
But you can include only to the ground state, well, so different type of
Yeah,
level, but only in the ground state, right?
Yeah.
For sure.
I haven't looked at NWChem.
yeah, I don't know. They always answer that they are working on it.
Any other questions?
If you're asking for a question yourself, then you need to announce a round of applause yourself.
Oh,
That's right. And there is one more talk. So it's literature club. So if you
I'm really bad at that. Bring that down.
one light. Yeah.
Not that way. That one.
The back, maybe the back.
No, I think
Okay. Yeah, definitely this screen is better.
That screen is definitely
Maybe
better
use
between
yeah,
these
use
two.
maybe this one when you if you need to explain something, use this one.
Okay. So what paper I was looking at was talking about conical intersections in lead halide perovskites and their non-radiative recombination rate.
This is a paper.
No, it's his slides.
So the group, they were looking at two different models, and the difference between them is that this is what they were terming the cluster model, and then they had what they were terming as the nanoparticle model, which is just 4 of the cluster models put together. And this is just lead, cesium, and bromide perovskite. And they so they were using state average complete active space self consistent field level of theory for their calculations.
Any introduction, what does it mean? At least just very simple kind of explain on fingers.
trying to figure that one out, and I really couldn't figure that model out.
So can I ask? Oh, you can go.
Why are you interested in this? What is
So
the goal?
so what they're looking at?
Who's there?
It's a literature
It's
club.
a literature review.
He's
It's
reviewing
a
the
group
paper?
from it was either University of Michigan or Michigan
Okay.
State. I don't offhand remember which right
And
now.
they're experimentalists, they're theoreticians.
They are
The paper is on
the paper is on theory. They
Okay.
do supplement it with some experiment.
Okay.
Um,
So
So what is the goal? You.
So the goal is they're looking at reasons. So lead halide, lead bromide. Why am I missing one? Cesium, lead bromide. Perovskites have a relatively low rate of non-radiative recombination, and they are looking at a possible reason for this.
so what is a conical intersection?
Conical intersection is a point where two potential energy states or surfaces from an excited state and the ground state where they would meet.
So it has to be ground and excited.
Or
I
too
don't
excited.
know if it has to be.
Would too excited would work?
I believe too excited would work, but I'm not sure of that.
But it's also possible that if you have a conical interaction between ground and excited state, right?
Yes,
Then again,
and
you will not.
that's what they're looking at, is between the ground state and the excited state.
Then I'm kind of confused. My understanding is low non-radiative recombination rate means that they recombine. Radiatively means they shine light,
Yes,
right?
yes,
So we really want that non-radiative recombination rate should be low.
Yep.
If we're interested in emitting materials.
yes, and that's what they're interested in. So it is low, and they're
Then conical intersection should not come from the ground to the excited state. Otherwise, if you
Yeah,
excite and then it immediately returns back to the ground state, right? So
Yep.
without not really shining the light.
yeah. So they do see that they have these. They're just energetically unfavorable.
Okay. So actually, yeah.
They would
So
like
in other
to.
words, they explain why these guys really shine light so nicely.
That's the goal.
Is it right to say that they're trying to find absence of conical intersection?
It's not that they're trying to find absence of them. It's that they were trying to explain. It's they found absence within a range where they would be energetically
Mhm.
active or energetically favorable.
Mhm.
And this is in regards to emission?
What?
To emission?
Yes.
Okay. So no absorption, just emission.
Yeah, this is emission.
So returning back to our previous question.
Yeah.
With this, you can go to this plot of red guys. So you kind of announced that they use this
State average,
active layer.
State average.
reactive space, something or other.
Yeah.
So how is it different? Like we know Hartree fork probably, right? We
Yeah.
know DFT and time-dependent DFT. We know what else we know?
CIS or
CIS,
CI.
right? Single or whatever how it calls conformational interaction space configuration, either singlet or doublets or whatever you can include. How this method relates to all these things which we know already.
So
is it better than Hartree fork?
It fills some gaps that Hartree Fock has.
What are
ones?
those gaps?
Which ones?
The
Does these gaps are covered by TDDT? If you compare TDDT with Hartree fork.
honestly not sure about that one.
So what is a conical intersection again?
Conical intersection is the point where a potential energy surface from an excited state and a lower state.
So crossing of two states.
Yes, cross where they would meet.
Is that well defined by a single determinant?
No.
So you need many body treatment
Yeah.
of your excited state, right?
Yes.
Is it introduced into the Hartree fork?
No. Hartree Fock does not use that.
Okay. Is it introduced in the TDDT?
My understanding of TDTFT is not.
Yes, it is not.
I'm not quite 100% sure on that one yet.
Again, you can think that you treat your kind of many body as a perturbation term, and again, it's only first order kind of contribution to your ground state, right? Which definitely probably not enough for very accurate calculations. And then if you go to the CI, which is CI configurational interaction space, right, or whatever it's called, configuration interaction space method. How is it different from the other approaches?
What approach?
CI, SCI, DCI, and so on. And actually, this method is kind of based on the CI as well. No idea.
I do not know.
See, here is the problem. When you kind of go to the paper, which is theoretical paper, and you have no ideas why they use this method, right? So it's kind of strange. That what's the purpose really to present this paper? Why did you choose this paper? If you don't know half of basics for what they're doing already, right?
Mm-hmm.
Anyone can help, maybe, except Dmitry.
You had no choice.
Okay, I got it. Tell us why you produced this left figure and what is it supposed to tell us?
So what this left figure is telling us is that as it's showing us the energy difference between the excited state and the ground state as time.
As your material you just showed us, that
so
system. Okay.
Right, yeah.
So are they a single calculation?
So this is 20 calculations.
So the trajectories of empty runs.
Yeah.
And some go to zero and some
Yeah, around 1200 femtoseconds they start splitting. Some of them start going to zero. Some of them are around 2.5.
Did the paper that you are citing, did they have this kind of figure?
This is from the paper.
Oh, this is from the paper. Okay, that
Everything is from the paper, right?
Yes.
citations at the bottom.
if everything is from a paper.
Well, I mean, just
Just one big citation,
one big citation. Okay.
repeated in each slide.
Do you
Okay.
if this is not a figure, this is where I got confused. This is not a figure you made.
No.
Why did they make this figure? Why was it interesting to you? Why did you think it's interesting?
To answer this question, we need really to understand the theory, and this piece is completely missing from
Okay.
presenter. Right? Or maybe I'm wrong, maybe it's wrong.
Same.
So to get this crossing, right, or whatever it's in the announcement of your title.
Yeah.
Can you get this just from the stationary calculations?
No.
So first thing, you need to do really dynamics.
Yes, and they are.
So you need to treat your excited state as accurate as possible. Plus, you need to really kind of let this excited state to move or to evolve with time.
Yeah.
So it requires dynamics. And you need to go beyond just a single excited state because at least two states has to be crossing, right?
Yes.
So which means you probably also need to go beyond just Born-Oppenheim approximation. You need to include some coupling with phonons as well, which I'm not sure is it involved or not in this treatment. It probably should. I mean, otherwise you will not get this result without really. So you need high order level of theory to calculate excited state. You need to include interaction with vibrations, go beyond Born-Oppenheim approximation, and plus you need, of course, do the dynamics with time. Means you really probably go through long time for the trajectories to wait until something happens. Right?
So, do you know if they treat each trajectory independently, or if they do what, like, kind of your group does and what we do for non-adiabatic dynamics, where we have a very long trajectory, we chop it up, and then we run the excited state dynamics? Or do they say, here's 500 initial conditions, and run each condition separately?
The way I understood it is that they were running each condition separately.
So if they did that, do you think it's statistically relevant? The number of initial conditions is statistically relevant.
And what is the number again? How many trajectories is involved?
20.
Well, the answer is not. Because you typically need to go to 100.
But why is it not? Looking at the figure on the right.
The figure on the right. Because they move and change at different points in time.
It's like a step function.
Yeah.
And it's weird.
And so if you look at it, the dark ones, it's like a light one, the darker lines are the average of it.
Yeah. But it's like very
And
jagged.
yeah, it's jagged and it happens at different times throughout.
But it's molecule, right? Oh, no, it's molecule.
It's population.
The dark lines are the average.
No, my point is, you might expect this if your levels are have a very discrete levels, right? If the split in between levels is very big,
Yep.
which is probably not the case for the clusters which you consider.
No. And
Okay.
Can I contribute so that we have constructive discussion? So there were questions about level of calculation of electronic structure and another about the transitions between electronic states.
Mm-hmm.
So since excited states are involved and system is small enough, they use multi-configurational approach, which means usually when we assume that there is a set of molecular orbitals, each of them have occupations, and then one forms one Slater determinant by making product of all occupied orbitals, which will be electronic state. But if there are excited states, which can be degenerate, there are several ways how excited state can be created by promoting different electrons from different occupied to different unoccupied. And such promotion from unoccupied to unoccupied sets a configuration out of which we create Slater determinant. And then several such promotions will create several Slater determinants which needs to be added together and form the wave function that is used here. So this is very expensive procedure, although it is generally correct. And it is typically applied to very, very small models only. So this is about the electronic structure. The second wave of questions was about trajectories and transitions. Neither one of the offers that Levi suggested, like whether it is one trajectory or several trajectories, was correct. Neither one. It is the third option, and it's the only thing which is critically important and cool in this work. They have splitting of trajectory. You start with one trajectory, and then as long as you jump between, you have probability to jump between potential energy surface, it creates offspring and continues two trajectories instead of one.
So it's like wave function, wave packet dynamics.
Yes.
Kind of
Yes.
nature.
Yes. And they call it a multiple spawning
Okay.
method.
This one, right?
Yeah.
It's kind of
So
illustration.
the pink dots here are the locations where they spawn, where more wave packets spawned.
So they spawn on S0? Because it says spawn to S0.
So the lines start at the initial state and they work down, and at these points, these pink points, are where the non-adiabatic factors required come into play in it.
Yeah, my question is, when they spawn it, where do they put it? Do they put it on the ground state? Because it says spawn to S0. So in my brain, that means when they make two, one goes to S0 and the other one goes somewhere else. Is that what's happening, or is that not what's happening?
From my understanding of how it works, is it spawns at the same location.
What Levi is asking, likely, if they are considering dynamics with initial state in S1, excited state,
Yeah, this
and
is
then,
their initial state.
and then they consider probability to transfer to the ground state from S1 to S0, right?
Yeah.
But they consider probability when it is not 100% transfer to S0, but there is
At some threshold.
trajectory diverges, and one trajectory offspring continues in S0, and another continues to develop in S1.
So then, does that mean that this just makes trajectories on the ground state, and it just keeps
It starts trajectories on first excited state,
Yes.
and then it makes offsprings to the ground state.
So it keeps a fixed number in the excited state, and it just generates more and more in the ground state.
In this situation, it looks this way, but
And then just
generally,
two states?
yes, but generally,
No, there's more than.
generally,
the last one it had. Can you go back a slide?
Yeah.
So it has 2 through 4.
maybe they.
So they did have some population in states above state 1 up here, somewhere around.
So at least
2000
up to 4
seconds.
states, right? So they considered 4 states. At least.
But everything that they placed it in was they started in S1
Did they explain why?
because that was the state they were looking at. That was the transition they were trying to look at.
That's okay.
They were looking at the S0 to S1 transition.
This is the excitation goes, right?
What?
This is where you on the S1. This is where you excite.
So this is more or less your take on this paper. It's like a lit review presentation, right?
Yes.
Yeah.
Okay, sorry.
Okay. That is still unclear, right?
And the first left figure on this left panel on this figure looks very counterintuitive and surprising. So S1 minus S0 is typically like band gap, lowest excitation, right? And they run a swirl of trajectories, and some of trajectories show that the band gap oscillates near 2 eV, and some of trajectories show that it just dumps to 0. So that lowest, like the system could be a semiconductor with 2 eV gap, or it could be metal or like gapless system. And very unusual.
Where this paper is published? It is not published.
Oh, it's not published. Oh,
So they. So this.
Since it's not published, but at least their methodology was published somewhere else.
Their
not in this
methodology was published. The non-adiabatic molecular dynamics they used was published in. I looked this up. I want to say the 80s. I looked at the actual.
Background
paper.
theory may have been developed.
It might have been
in
the
areas,
theory
but
that I was
computational
looking at.
implementation cannot be
Yeah.
so old because it's quite expensive.
I was looking at the background
No,
theory.
they
paper.
use some
But
kind
they
of
did, yeah.
their own codes, right?
Yeah.
To do this.
But yeah, the theory they based it off of has been around for a few decades. So here they show the orbitals for their primary cluster molecule, and the point of this was to just give an idea of whether their system was working.
So what does N mean?
N is the orbital, and I could not understand why it's partial.
Then it's not all.
Every single one of their orbitals or their diagrams in here had one with N approximately 1.5 and one with it approximately 0.5.
Maybe it's population.
It-
I'll say charge density or something.
It said in the paper that N equals it said N equals 1.5 and they listed that as orbital, but I could not find anything to indicate why it would be a partial number. I was actually hoping you might be able to explain that to me. So then the models that they actually looked at, so these are all, here's the model that we saw earlier. So what they had is they have one where they took one of the bromines away from the lead atom, one of the cesiums away from the lead, one where they took both the cesium and the bromine away, and then these two they distorted the molecules. In this one they distorted several cesium and bromide molecules away from the lead.
Question: was it forced manually prepared to deprive a couple of atoms away
Yes.
from the cluster, or it was result of molecular dynamics?
It was forced.
Okay.
And this one they distort two of the bromines.
Okay.
So what are the notations on top?
This one they distort two of the bromines. This one they distort several.
What is BRDCI?
So the BRD stands for bromine dissociated,
Okay.
cesium dissociated, cesium bromine dissociated, double bromine stretch, and I think they called that ballooned, but that one was multiple atoms were distorted.
So why did they do this?
Because they were looking to try and find in what orientation it was more likely to get the conical intersections.
What
So
kind
you-
of motion? of
Which
atoms?
geometry makes S1 minus S naught gap equals 0?
Yeah.
Yes. Or at least closer to 0.
But then why would they change it so dramatically?
Change geometry or what?
Yeah, like these are like
Oh, they want to go to the limiting case.
okay.
I guess. You're saying why it's not just perturbed but completely taken off?
Mm-hmm.
So
But they do get perturbed as well, right?
these two are perturbed, where these three are completely removed,
Okay.
or at a distance where they were assuming it was completely
I guess they
removed.
just kind of create a limiting case to send something in between. Right?
These ones were specifically greater than 7 angstroms away from the lead. These ones are less than, between the 3.5 and 7 angstroms.
Sorry, I have to go.
here they prepared and showed the energies for several of for these different compounds. And they have all the different, they used a few different levels of theory to calculate it, and they have several of them listed.
So what does abbreviation CASPT2 stands for?
Which one?
In the legend, they have repeating CASPT2 with some additional index. Do they?
This one?
Yeah. Do they explain this abbreviation?
MS CASPT2 is multi-state complete
active space.
Active space second order perturbation theory.
Okay.
And FOMA?
FOMO is floating orbital molecular. No. I don't remember what the first O is.
Okay.
Could it be like a generalization of HOMO and LUMA, where HOMO and LUMA are completely occupied, completely unoccupied, and this can be like with partial occupation? No? Or frontier orbital?
The way I understood it is your first indication is more correct.
Okay, so fractional occupation, molecular orbital.
So maybe that's why they have fractional, like 1.5.
So it's occupation of this orbital.
Yeah.
Interesting. Oh, it is.
how is it
Well, it
1.5?
is we often see in VASP for metals.
But why is it?
Due to the
Oh,
distribution.
maximum then is 2, not 1?
Yeah, because you have 2 electrons that are in the frontier orbital.
So in here we're looking at the potential energy surface is calculated for the standard cluster molecule, not standard, the bromine distorted molecule or atom, and if as you pull the bromine farther away from the lead, it increases, and the potential energy surface for the first excited state meets the ground excited state around 9 angstroms. While over here we have the Mulliken charge for the same system, and we have them approximately equal at the same point.
So this conical intersection and consequently very quick recombination from excited to ground will occur only if kinetic energy is high enough to extend bromine to lead distance from 3 angstrom to like 8 angstrom.
3 to 8,
So
3 to 8, 9.
It needs to be really
And they did
high temperature.
They did see that their best case for conical intersection was in the one where the bromine was distorted. So here we see a couple more models, and we're looking at this pair is the bromine, this dissociated. Well, this one is just another set with the normal perovskite. And on this side, we're looking at 2 of the clusters, or not the clusters, it's nanoparticle models. And they were looking at how the orbital here are on different lead atoms, which was one of their theories on why non-radiative is less likely to occur because it's geometrically unfavorable in the nanoparticle size. So this is similar to the ones we had for the cluster particles. This is there are different nanoparticle models. We once again have a bromine dissociated, a cesium dissociated, and a stretching distortion molecule. And here we also see another energy diagram for the nanoparticle energies. The previous one was for the cluster energies. And this purple line here is a reference experimental value for the band gap.
So was the band gap experimentally for the same size systems or bulk?
It was for bulk.
So, things like, yeah. So how you relate the S1 energy and S1 energy with the bromine lag distance one is higher than
So when it's higher than 10, it starts to increase a little bit again.
but if
The
there are no
separation.
interactions between bromine and lag, right?
There's going to be little interaction involved.
That's how
Yeah, there's going to be little to none at that distance.
I think what happens maybe is when you pull them apart, the wave function has to determine where the electron's going to go. So when they're together, they're happy, and then like when you do orbital mixing in like inorganic chemistry, you get the two states split, and as you pull it further and further apart, the coupling gets smaller and
what
smaller.
is the problem? Or how long distance you can consider the interaction?
Obviously, all the way to 14, since 14 is still changing the energy.
Maybe it's not because of that bromine lag distance, something happening on the cluster, so that's changed the single one or silicon state, but not
Yeah,
not because of this distance.
but I think if they did it intelligently, they would have optimized everything except the distance. So then, having to think further away, the cluster itself would still minimize the energy, like it would like realistically. So pulling it away still has effects on both of them, which I think if he was showing like n, if we think n is the occupation, n is it varies, right? So as you pull it away, it still plays with the cluster.
How bromine atom can play on the cluster when the distance is 10 and things. No, I'm just wondering, I don't know, maybe they have
Looking at his data, it has to.
They didn't have any explanation. They just assumed it just kept going farther.
Electrostatic is yet active on this distance. Although in many of our calculations we assume that 10 angstrom will kill any interactions. But these guys could be very meticulous and use some very generous basis set with a lot of
What program did
orbitals. They
MOPO.
Is that fine wave?
no. It's atomic basis set
Oh.
with far-going tails.
Oh.
That's the basis set they use for the nanoparticle.
Okay, so other is it
Are there
last
any
slide?
conclusions or what? Are we done?
So right here, one of the things they were looking at, you see that many of the energies are above for the conical intersection are above the experimental value, which they assumed and concluded that it meant that they were energetically unfavorable to actually occur.
But wouldn't confinement effects play with this result?
Oh, they are molecules, they're not really.
Confinement would be like less than half EV, or maybe like 1 EV, and here the jumps from 0 to 6, it is more on the interatomic bond lengths, which they change drastically.
Oh, so
the
you're
X,
saying relative to black, the cyan dashed and the red and orange?
Yeah,
Those are, okay, that makes sense then.
Like different methods give some details, right? You have a little bit different kind of splitting between these levels, but in overall, right? So the results are consistent among the methods. Like they're all showing significant splitting for all these molecules, except for all of them. What
except
about
for
this one? Yeah.
This one is the standard normal shaped molecule, so the when it's not distorted or has anything removed. And so I remember how they explained that. That one is what gives us the normal experimental photon emission, isn't it?
Yeah.
Where these distorted ones, where the conical interface are more likely to happen, are all above the normal excitation amount.
Okay, so through this modeling, they conclude that intersection happens.
They conclude that they happen, but they're not energetically favorable to happen.
So they happen rarely, therefore excited state has long non-radiative lifetime.
Yes, and they did show here that some of them do go to 0.
Did they relate it to fusion?
No.
Because they are ionic conductors, so if there's defects, then you can have a bromine pop from one side to another, and where you show that bond distance. That would, yeah, so like their normal bond distance.
Oh,
Because
like,
even if that pops, like you're probably only going like
you mean
5.
Permutation? One bromine departs, another comes to the same spot.
So it's like you get some bond distance increase that way, but based on the results, it doesn't seem to.
But probably they manually departed it far.
Right, but I mean like in a realistic situation.
Yep.
Yeah, they
don't
manually
include.
moved it for this.
That's it? Okay, well, thank you. Really interesting results. Thank you for being brave and showing it. And the conclusion is that it's not possible to use this method for larger systems, but in some circles, communities, it's considered as golden
Кругам,
standard.
которым я близок, мама. Дмитрий говорит, in some circles, кругам, которым я
Okay, thanks
близок.
for coming and those who travel have a
Митя, у
safe
вас как там дела?
Да нормально, ну что ты так закопался, я во всех этих административных
Oh, yeah, we have to.
не кончается.
В смысле, что это там? А из-за студентов?
Постоянно какие-то заседания, не...
Заседание? То есть ты, только, ну, зачем ты, наверное, записался слишком много комиссий.